Hello students, our next chapter is motion in the central force field. Our study on the central force began with the planetary motion. It began with the studies in planetary motion. You know that Tycho Brahe was the scientist who studied about the motion of planets around Sun. It was before the invention of a telescope, and later after his death the telescope was invented, and Kepler was the person who studied for many years on his calculations, Tycho Brahe's calculations, and finally three laws were formulated related to the planetary motion, which was popularly known as Kepler's laws of planetary motion. There were three laws. The first one is every planet moves in an ellipse with the Sun at one focus. The second is the radius vector from the Sun to the planet sweeps equal areas in equal times. And the third one is the period of revolution t of a planet about the Sun is related to the major axis A of the ellipse by the relation t square is equal to k aq, where k is a constant which is the same for all the planets. These three laws were empirically formulated by Kepler by the findings from Tycho Brahe, right? Later, after many years, Newton found out his general features of interacting particles and the mechanics. He started applying Newton's mechanics to the general problem of central force motion. So in this chapter we will be studying the central force motion. So the general features of the system of two particles interacting with a central force f of r, unit vector r, where f of r is a function of the distance r between the particles and unit vector r is along the line of the centers. So these are the features of our central force. So it is among two particles interacting with a central force f of r. It is along the distance of r, along the direction of r, where r is a unit vector along the line of centers. Okay, this will be studied in detail in this chapter. After making a simple change of the coordinates, we shall show how to find a complete solution by using conservation laws of energy and angular momentum. Finally, we apply these results to the planetary motion. F of r is proportional to 1 by r square, and show how they predict Kepler's laws. Right? These are the things we are going to find in our chapter. Now, we are finding central force motion as a one body problem. We know that actually the central force motion is a two body problem, two interacting particles. This can be completely converted into a one body problem. In this video we will be looking this translation of a two body problem into a one body problem is taken. So our system contains two particles m1 and m2. This is the direction of r. This is the vector r1 and r2 of the position of m1 and m2. These r1, r2 and r are related by the relation vector r is equal to r1 minus r2. You know the triangle law of addition. From that you get r is equal to r1 minus r2, or the value of magnitude of r is equal to magnitude of r vector, which is equal to r1 minus r2. Okay, so these two particles are interacting under a central force f of r in the unit vector r direction. Okay, now we have two equations of motion for m1 and m2. They are m1 r1 double dot, or the acceleration of m1 is equal to f of r unit vector r, and m2 r2 double dot. R2 double dot is nothing but the acceleration of m2, that is equal to opposite direction of this value, it is minus f of r unit vector r. So we know that f of r is less than 0 means the force is attractive, and if f of r is greater than 0, the force is repulsive. Now the equations, these two equations 10.1a and 1b, are coupled together by the relation by the vector r. Okay, now we are trying to find out how can we relate these two equations, or how can we convert these two equations and combine them in the form of r. Okay, you know the relation r is equal to r1 minus r2. So the problem becomes easier if we replace r1 and r2 by r is equal to r1 minus r2. Now we define a center of mass vector r is equal to m1 r1 plus m2 r2 by m1 plus m2. This is the position of the center of mass of that two particles m1 and m2. Okay. Now for if there is no external forces, you know that the equation of center of mass r double dot is equal to 0. Okay, the solution of this equation will be r is equal to r0 plus vt. The constant vectors r0 and v depends on the choice of the coordinate system and the initial condition. So if we choose the origin at the center of mass, then r0 will be 0, and if the center of mass is held stationary, we can take v is also 0. This is this depends on our choice of the coordinate system. Now the equation for r turns out to be like the equation of motion of a single particle and has a straightforward solution. So we will divide our first equation 10.1a by m1 and 10.1b by m2 and subtract that two equations. You get r1 double dot minus r2 double dot is equal to 1 by m1 plus 1 by m2 f of r unit vector r. Or on solving and rearranging, you take these things on the towards the left hand side, you get m1 m1 plus m2 into r1 double dot minus r2 double dot is equal to f of r unit vector r. So by denoting m1 m2 by m1 plus m2 by mu, which is called the reduced mass, mu is the reduced mass, and r1 double dot minus r2 double dot is replaced by r double dot, we can rewrite the above equation as mu r double dot is equal to f of r unit vector r. So this equation is identical to the equation of motion for a single particle of mass mu acted upon by a force f of r. So there is no trace of a two particles problem in this equation. So we have transformed a two particle system into a one particle problem. Okay, so we have introduced a reduced mass and the difference between the two vectors, and we have framed a relation which is similar to a one body problem from two interacting particles. So this is our figure of, this is our center of mass r, and these are the two vectors. These two vectors are related to r1 and r2 by these relations. Okay, these are the relative positions of m1 and m2 from r actually. So we can treat a two body problem into a one body problem by the concept of a center of mass. Okay, thank you.